Welcome to section 5.3. 5.3 is going to be very similar to what we've done in the past. We've done separation of variables. This is a little more practice with that. I normally do this kind of as a class project and just kind of have everybody working on these problems instead of lecturing at it. So go through the examples here. I'm not going to require you to turn in notes necessarily, but you do want to make sure that you go through each of the examples, especially at the end or toward the latter of them, because they do get a little more complicated and give you some more things to maybe think about. So separation of variables, kind of a day two, but not really kind of, just because of the way the sections work here. So remember, separation of variables, we want to get all of our variables alike on one side. So that means if we have a dy on the left side, we want all of our y's on the left side and dx's on the right side. Normally we want our y's on the left and x's on the right. So let's go ahead and solve x y prime equals y. So the first thing I want to do is change this y prime to dy dx. So I have x dy dx equals my y. Now I want to get my x's to the right side and my y to the left side. So I'm going to divide by y, and that gives me 1 over y dy dx. And I'm going to divide by x, so I get 1 over x, and I multiply my dx over. So I get 1 over y dy dx equals 1 over x dx. From here I can go ahead then and solve. I can integrate both of my terms there. So the natural log of y plus c equals the natural log of x plus our c. Now I can go ahead and bring my c over. So I have the natural log of y equals the natural log of x plus c. In order to get that natural log out of there, I can take an e to the both sides. So I have e to the, I don't need that equal sign, e to the natural log of x plus c, and that's going to equal my y value. Now this over here, this becomes a little more cumbersome, I guess, or thinking there. We have that plus c. Remember that plus c, we can break that up into e to the natural log of x times e to the c equals y. E to the c is c, so I have c e to the natural log of x equals y. E to the natural log of x, remember e and natural log, they are inverses of each other, so we're going to get just x. So we're going to get the equation y equals c times x. And that's going to be our solution. In our next problem, we already have our y's on one side. We just got to get that dy or dx over to the right side. So we're going to change that that y prime to dy dx. And that's going to equal 6 cosines of pi x. Multiply my dx over, so y dy equals 6 cosines of pi x dx. And we'll go ahead and integrate both sides. So that gives me y squared over 2 plus c. It's going to equal the integration over here. If I take the cosine of an angle, I can only have a single variable. So I'll let my u equal pi x. So du equals pi dx. I can't use that pi in my integrand. So I have 1 over pi du equals dx. So that gives us the integration of 6 over pi cosine of u du. And I know the cosine, integration of cosine of u. So I have y squared over 2 plus c equals 6 over pi, that's a constant. And an integration of cosine, that's going to be sine of my u, which is pi x plus my c. Again, that plus c and this plus c can come over. They don't cancel. Of course, they don't cancel. They're just going to combine into another different c. And now I'm going to go ahead and solve for y. So I'm going to multiply by 2 and then take the square root. So y is going to equal plus or minus the square root of 12 over pi sine of pi x plus c. And that's going to give us our answer. All right. We have more problems. We had another page that's stuck in there. So here's a radical problem here. We have the square root of x squared minus 9y prime equals 5x. So again, I'm going to change that to dy dx. and move my dx over, and also my x squared minus 9 square root needs to go over. So I get dy is going to equal 5x over the square root of x squared minus 9 dx. I can go ahead and integrate both sides. The integration of dy is going to be 1y plus c. Integration over here, I'm going to let my u equal x squared minus 9. So du is going to equal 2x dx. I can't use the 2, but I can use the x. So we have 1/2 du equals x dx. Go ahead and bring that into my integrand. I can bring that 5/2 to the outside. That 5 comes out, and this 1/2 comes in with it, or goes out with it. My x dx goes away as a 1 over u to the 1/2 du. In order to integrate that, I'm going to bring that to the numerator as a negative exponent. So I get u to the negative 1/2. So I have y plus c equals 5/2 u to the 1/2 divided by 1/2 plus my c. Cleaning that up, I have 5/2. If I divide by 1/2, that's the same as multiplying by 2. So I actually get just 5. And then my u value, which is x squared minus 9 to the 1/2 plus my c. Again, when I bring my c over, I have my c there. And there's my answer. I have y by itself already. I've solved it. Yay! All right, here we have the square root of x plus the square root of y prime equals 0. But we're also given the information y of 1 equals 4. So, what does that mean? Well, we can go ahead then and solve. We can bring our dy or y prime into a dy dx and bring that x over. So I have the square root of y equals a negative square root of x dx. Now I can go ahead and integrate both sides. Oh, that's my dy there. So this is y to the 1/2 dy, and this is x to the 1/2 dx. And I'm going to be integrating. I can definitely integrate y to the 1/2. That's y to the 3/2 over 3/2, which becomes 2/3 plus our c. And same thing with our x. We get x to the 3/2 over 3/2 becomes 2/3 plus c. Now we can go ahead and subtract that c over. So we have 2/3 y to the 3/2 is going to equal negative 2/3 x to the 3/2 plus our c value. But we know that y of 1 equals 4. So I plug in 4 for my y value. I'm going to get 1 out for my x value. So I end up with 2/3 y, which is my 4 to the 3/2, is going to equal negative 2/3 of 1 to the 3/2 plus c. 4 to the 3/2. Remember, we like to take the root of it first before we take it to the exponent. So 4 to the 1/2, that's 2 to the 3rd, which gives us 8. And then 8 times 2/3, that's going to give us 16/3. And that's going to equal, we have 1 to the 3/2, which is 1 times negative 2/3. So we get a negative 2/3 plus c. Add that over. If we add 2/3 to 16/3, we get 18/3, which is 6. And that's going to equal our c value. So we know that our c value is 6. So we have 2/3 of y to the 3/2 equals negative 2/3 x to the 3/2 plus c. Now we can go ahead and solve for y. So we can, we don't remember a 6. We need a 6 there, not c. So now we can go ahead and multiply both sides by 3/2 to get rid of that 2/3. So we get y to the 3/2 is going to equal negative x to the 3/2. And then 3/2 times 6 is going to be 18/2, which is 9. And then we're going to get rid of that exponent for our y. So we're going to take that to the 2/3 power. So we get negative x to the 3/2 plus 9 to the 2/3. And that's going to be our answer. All right. Focus that in. There we go. A little better focus. All right. So here we have something that looks a little more ugly. We have y times the square root of 1 minus x squared, y prime, minus x times the square root of 1 minus y squared equals 0. Y of 0 again equals 1. So what do we got? Well, we got to get this dy dx in there. And we're going to move this stuff over to the right. So we have y square roots of 1 minus x squared dy dx. We might as well put that in there. Equals, if I add that over, I get x square roots of 1 minus y squared. I can go ahead and multiply my dx over. Now I've got y is on the right side and x is on the left side, so I'm going to divide those out. So if you bear with me there, we get y over 1 minus y squared dy, and that's going to equal x over the square root of 1 minus x squared dx. So I did a lot of algebra there without showing it. So I divided this square root of 1 minus y squared over, divided this 1 minus x squared over, and brought my dx over. Now I can go ahead and integrate both sides. Here I'm going to let u equal 1 minus y squared, so du equals a negative 2y dy. I can use that y, but I can't use that negative 2, so I have a negative 1/2 du equals y dy. So that gives us an integration, negative 1/2, the integration of 1 over u to the 1/2 du. Same thing's going to happen over here. I really don't want to use a u though, do I? Probably want to use a v. So let's let v equal 1 minus x squared. So dv is going to equal a negative 2x dx. And again, I can't use that negative 2. So I bring that over, negative 1/2 du, or dv, equals x dx. So I've got the integration of my negative 1/2, the integration of 1 over v to the 1/2 dv. I can't integrate in our denominator, so I'm going to bring that to the top as a negative exponent, and bring this v to the top as a negative exponent as well. So the integration then, we have negative 1/2 of u to the 1/2 over 1/2 plus our c. That's going to equal a 1/2 times v to the 1/2 over 1/2 plus c. Our 1/2s are going to cancel very nicely on both sides. So we get a negative, I'm going to lose my room, negative u to the 1/2, and we'll bring my c over, equal to v to the 1/2 plus c. I can go ahead and replace my u with 1 minus y squared, so I have the negative of 1 minus y squared. And that's going to equal v, which is 1 minus x squared, to the 1/2 plus our c. Oh, I lost my 1/2, didn't I? There we go. Now we can go ahead and find our c. We know that x, when x is 0, our y value is 1. So when we plug in 1, we get 1 minus 1 to the 1/2 is going to equal 1 minus x, which is 0, to the 1/2 plus our c. 1 minus 1, that gives us 0, and that's going to equal 1 to the 1/2 plus c. So we have a negative 1 equals our c value. And I'm going to kind of stop it at that point. I'm going to assume that we can all go ahead and solve for y there, because I've run out of room. I'm out of room, minus r1. So in order to do that, we would divide by negative 1. Let's go ahead and do that down here, I guess. We have 1 minus y squared to the 1/2, and that's going to equal 1 minus x squared to the 1/2. And I can go ahead and square both sides. So we have 1 minus y squared equals 1 minus x squared to the 1/2 squared. And I can subtract my 1 and then divide by a negative 1 and take the square root to get our y by itself. I'm not going to do that necessarily because I want to get into this problem and have enough room for it. So here, dr ds equals e to the r minus 2s. So here, this one actually becomes a little more complicated, a little bit, although we should realize from what we've done in the past how to break up e to a couple of variables or a couple of exponents there. we can break that up into a multiplication problem. So we have e to the r times e to the negative 2s ds. We can go ahead and bring this e to the r over. So we have e to the, if I divide by e to the r, that's the same as e to the negative r dr equals e to the negative 2s ds. Integration of e to the negative r, we can't necessarily do that, so we let u equal a negative r. So du equals a negative dr. And a negative du then equals dr. So we have the negative integration of e to the u, and that's going to equal, same thing's going to happen over here. We let v equal a negative 2s. So dv equals a negative 2 ds. We can't use that, so we have a negative 1/2 dv equals ds. So we have a negative 1/2 the integration of e to the v dv. And we need our du there. Integration of e to the u, we know, is e to the u, so we have e to the negative r is going to equal a negative 1/2 e to the v, which is negative 2s plus rc. Now we're going to plug in 0 for r and s, since we know r0 equals 0. So we have negative e to the 0 equals negative 1/2 e to the 0 plus c. So if I go ahead and solve for c, I get negative 1 equals negative 1/2 plus c. Add my 1/2 over, I get negative 1/2 equals c. So I get negative e to the negative r equals negative 1/2 e to the negative 2s minus 1/2. Now I'm going to go ahead and get me a sheet of paper here, because I want to go ahead and continue this on.